Hey folks, today we're going to talk about the alternating series test, which is also known as the Leibniz test. In a previous video, we proved the convergence of the alternating harmonic series. And our goal is to adapt the method of that proof to cover a more general class of series whose terms alternate in sign. So we're going to be able to show, for example, that this series and this series here are both convergent series. So you'll notice that these are examples of alternating series where the signs of the terms alternate. So you'll notice that the second series actually starts with a negative term. So it alternates signs negative, positive, whereas the first one's positive, negative. We're going to first state the alternating series test in a way that picks out the first case where we start on a positive first term. And that brings up a point about the whole theory of alternating series that obey the alternating series test. The ideas tend to be much simpler than the symbolic mechanisms we use to convey it. So talking about it and writing about it can look a lot more complicated than the actual theory is. So try to keep that in mind as we move forward. So here's our theorem. Suppose that pk is a strictly decreasing sequence of positive numbers that converges to 0. And then you build a series by alternating the signs. So it's p1 minus p2 plus p3, etc. So the theorem says that that series you build actually converges to some limiting value L. And then you'll notice that the partial sums alternately over and underestimate the value of L. And if sigma n is the nth partial sum, then the absolute value of sigma n minus L is always going to be less than p sub n plus 1. So let's look at that last inequality. It's rather interesting. If we think of a partial sum as an estimate of the actual value of the series, then this term represents sort of the error. How far is the partial sum from being equal to L? And what this relationship tells us is that this error is never worse than the magnitude of the next term of the series. So whatever it is you're about to subtract or add, you know that that length, that magnitude, is giving you a bound on how bad your current partial sum could possibly be estimating the actual value of the series. This is not something that usually happens with an infinite series. Usually you'd have to work a lot harder to know how close you are to approximating the actual value of a series. So this is an interesting feature of series that obey the alternating series test. So let's restate the theorem. Here's version 2, and let's say we're going into symbol overdrive here. So we're just going to say exactly the same thing, but we're going to use a lot of symbols. So these represent respectively the properties that the terms are all positive, they're strictly decreasing, and they converge to 0. And then we know that this series converges, and if you let the partial sum be represented here by sigma notation, then we know that sigma n is greater than L when n is odd, sigma n is less than L when n is even, and we get our error bound. Some people love using symbols, so you might like this slide better. I think it's a rather confusing cloud of symbols. Let's try version 3. Let's use pictures. So the idea here is if you start with a sequence of positive numbers that is strictly decreasing and converging to 0, and you build a series out of it by alternating every other sign, what happens is you're going to wind up with a sequence of partial sums that bounces back and forth in such a way that some of the partial sums are strictly decreasing, some of them are strictly increasing, but they both converge to a common limiting value L. And implicit in this picture are more of the properties we stated on the previous slide about how close each partial sum is to actually being equal to the value L. So let's prove this theorem. And we're going to do it in parts. And if you saw the video on the alternating harmonic series, these parts will look quite familiar. So the first claim is the subsequence of odd partial sums is decreasing. So the odd partial sums look like this. And the thing to notice is the very last thing you do is you subtract and then add these last two terms to get the new partial sums. So let's see if we can go for the general case in one fell swoop here. Let 2n plus 1 be any odd natural number greater than or equal to 3. The reason we're taking it greater than or equal to 3 is we're going to back up, so we want someplace to go, and that could be 1 possibly. So here is the 2n plus 1th partial sum in its full glory here. And what we'll notice is that right there is actually the previous odd partial sum. That's sigma 2n minus 1. And so we get this relationship here. And we're going to factor out the minus sign. And recall that the sequence of p sub k's is strictly decreasing. So p2n has to be larger than p2n plus 1. And that means the term inside this parentheses here is actually positive. And that means that sigma 2n minus 1 has to be larger than sigma 2n plus 1. So now what do we have? Here's some odd partial sum, and here's the very next odd partial sum. And that relationship tells us that the sequence of odd partial sums is strictly decreasing. Now, we also claim the subsequence of even partial sums is strictly increasing, and the proof is going to look very, very similar, and I will leave it to you as an exercise. So the next step, the odd partial sums are bounded below. What do we mean by this? We already know they're strictly decreasing. And if we could figure out a floor below which they do not go, then the monotone convergence theorem is going to tell us that this subsequence of odd partial sums actually has to converge. So this is a key step. We want to just show that the odd partial sums are bounded below. And so the proof looks like this. We'll notice that the even terms here are negative. We're subtracting off p sub k's. And so we'll let 2n minus 1 be any odd natural number. So when you calculate the next partial sum, sigma 2n, it would be the old partial sum, sigma 2n minus 1, minus p2n. So you're subtracting something off, and that means sigma 2n minus 1 has to be larger than sigma 2n. But then sigma 2n has to be greater than sigma 2. And that's because the sequence of even partial sums is increasing. So sigma 2 has to be smaller than any other even partial sum you could calculate. And what does that mean? That means because we chose any odd natural number here, we've just proved that all the odd partial sums are greater than sigma 2. So the sequence of odd partial sums is in fact bounded below by sigma 2. And in our picture, it's pretty clear why. You've got your subsequence of odd partial sums, and surely they're all going to be bounded below by this sigma 2. And you could find a better bound, but we don't need a better bound. We just need a bound for the monotone convergence theorem to kick in. So there's another claim, obviously. The even partial sums are bounded above by sigma 1, and in your picture, you can see that your odd partial sums should be bounded above by sigma 1, and you can prove it in a very similar manner. So now it's time for the monotone convergence theorem to kick in. The subsequence of odd partial sums converges, and the subsequence of even partial sums converges. Why is that true? Well, from what we've done and what was left for you as an exercise, we've proved that the odd partial sums are strictly decreasing and bounded below. The even partial sums are strictly increasing and bounded above, and then the monotone convergence theorem guarantees that both of those have to have limiting values. So where are we? We've got our sequence of partial sums. We know the odd partial sums converge to some limiting value. So do the even partial sums. Unfortunately, we don't know yet whether these two limiting values are the same. If they weren't the same, it would be trouble, because then the sequence of partial sums would start bouncing back and forth between two different values, essentially. And we need it to converge to a single value if we're going to claim that the original series converges. So the claim here is that the limiting value of the odd partial sums and the even partial sums agree with each other. They converge to the same value. So the proof is just to look at the difference of these two limits, apply the limit law that allows us to take the limit of the difference here, and notice that we're just taking successive partial sums, so the difference is just the term, but we know that the sequence of PNs converges to 0, and that just tells us that those original two limiting values are actually the same. So there's the proof of our claim. And so this diagram we can resolve. There's actually a single common limiting value. And now where does that put us? So this tells us that the series converges to some limiting value because the partial sums converge to something. And the partial sums, by what we've seen, they have to alternate between being greater or less than the value of L, because the odd partial sums are all lying on one side of L and strictly decreasing to the limit, and the even partial sums are strictly increasing to the limit, so they all have to lie below the limit. So let's explore the error-bound component of the theorem. Suppose we plotted the nth partial sum, and then to jump to the next partial sum, we'd have to say subtract off a term. And then to jump to the next partial sum, we'd have to add on the next term. And from what we've seen, we know that the limiting value has to lie somewhere in here. Let's translate this picture onto a number line. So what we'll do is we'll actually plot the value on a number line. So here's the partial sum sigma n. You're going to jump across to sigma n plus 1, and you're going to jump across the actual limiting value. So the argument I'm about to make should be sort of ambiguous about whether or not you're starting to the left or the right of L. Maybe we've overestimated with sigma n and we're about to jump to the left. The principle I'm about to describe is going to work in either case. So here we go. You look at this diagram and you realize that the distance between sigma n and L, which would be the absolute value of sigma n minus L, is clearly smaller than this amount we jumped. And so this is the error bound that was part of the statement of the alternating series test. And now here's a point that goes back to this idea that the notation often gets in the way of simple ideas. What if the alternating series has been described in a way that makes the sign of the terms ambiguous? So maybe we used plus signs, and the thought is now instead of alternately adding and subtracting positive terms, now we're just adding terms that alternate between positive and negative. So if that's the case, or maybe you just sort of lost track of whether you're adding or subtracting, you could have a situation where you really, just based on the general case, you're not quite sure whether you're jumping from the right to the left or the left to the right, whether you're adding or subtracting n plus 1. So there's some ambiguity here, but the good news is you can still state the principle of how well a partial sum approximates L quite easily. So here's how you do it. You just use an absolute value. So the absolute value of sigma n minus L is going to be less than the absolute value of an plus 1. Why does this work? Well, it doesn't matter which side you're on. Either you're measuring this distance or this distance with this term. But in either case, you're definitely going to be smaller than the magnitude of how far you jumped, whether or not you subtracted or added that term. So this error bound can be useful when your description of the series leaves you with some ambiguity about where you are, whether you've overestimated or underestimated. It's still going to work no matter which case you're talking about. So if we think of the nth partial sum as an estimate of the value of the series, then this is the error. And this relationship tells us that the error is never worse than the magnitude of the next term of the series. So as promised, this was the error-bound component of the alternating series test. So let's finish by, if you can believe it, looking at version 4 of our theorem. And this is the version that will often show up in textbooks. So suppose an is a sequence such that an alternates in signs, the absolute value of an is strictly decreasing, the limiting value of absolute value of an is 0, then the series converges to some L, the partial sums alternately over and underestimate L, and we have the error bound. Now, what is different about this version of the theorem? You'll notice that this actually allows for the first term to be negative because it's ambiguous. It just says the terms alternate in sign. It doesn't say that the first term is positive. So this is a slightly more general version of the theorem we stated before. And you might wonder, did our proof depend on starting off on a positive term? And essentially the answer is no, but we'll have more to say about that in a second. Let's look at some examples. So here was the first example we promised earlier. This is the alternating sum of the reciprocals of the square roots. So let's try to apply the criteria we just saw in the statement of the alternating series test. Do the terms alternate in signs? Well, that's certainly the case. Now let's switch over to the absolute value of the terms. So this is nice. We get to strip away the minus signs and just look at this simpler sequence. And now we have to ask ourselves, is it true that the limiting value of this sequence is 0? And that's certainly the case because root n goes to infinity. So when we reciprocate that, that's definitely going to go to 0. So we're good. Is it true that this sequence of absolute value of terms is strictly decreasing? That's also true because root n is strictly increasing and you reciprocate that and it's strictly decreasing. So the alternating series test tells us this series definitely converges. But it tells us more than just that it converges. We can actually do some calculations and be able to conclude some things. So fun fact, you can use Desmos or your calculator, but you can calculate, say, the 51st partial sum, and you're going to get this value here. Now, what can we do with this value? Well, you'll notice that the 51st term was a positive term. So to get this partial sum, the last thing we did was add something. What does that mean? It means that the actual value of the series has to be smaller than this. So whatever the series actually converges to, it's got to be smaller than sigma 51. But how close are we? Well, the next term that we would include, we'd actually subtract 1 over root 52, but the size, the magnitude of that is about 0.138675. So from this calculation, we know that sigma 51 can be no worse than that far away from the actual value of the series. So let's play around with this example a little bit more. At what point can we guarantee that the partial sum is within 0.001 of the limiting value of the series? Well, we have the error bound, and we know in this case that the magnitude of the next term we would add is 1 over square root of n plus 1. And we'd like that error bound to be no worse than 1 over 1,000. So what we're going to do is we're going to choose n to make this true. So here's the inequality that we're going to focus on. How can we guarantee that this is true? Well, we're going to reciprocate and flip the direction of the inequality, square both sides, subtract 1, and apparently if we choose n to be greater than or equal to 999,999, we will have guaranteed that the partial sum is within 0.001 of the actual value of the series. Now this is again is something you can do on Desmos. Here's your 999,999th partial sum. And the theory tells us, based on our choice of n, that this should be accurate to the nearest 0.001. Now, I went on to Wolfram Alpha and I asked it to evaluate the infinite series, and it gave me the limiting value was about equal to 0.60489. The partial sum we calculated is in fact within 0.001 of the actual value of the series. All right, example B. Now, what's intriguing about this example is that the first term is negative. And you might think, oh no, we have to go back and reprove this case and look at all the changes that occurred in the theorem. But we're not going to do that, and we're just going to imagine why the proof that we laid out earlier is essentially going to cover this case as well. So here's the big conceptual way to see that this really doesn't introduce anything that's qualitatively new. Remember that we can factor scalars from series, and factoring scalars doesn't change the convergence property. So if we just factor out a -1 from the whole series, we recover a series that is alternating and, as we shall see, obeys the hypotheses of the alternating series test and starts with a positive term. So all the work we did before essentially covers this case. So there's really no need to hack through another proof for alternating series that start on a negative sign. And then as far as the conclusions go, we might have to adjust them slightly. So basically your picture is flipped because your first term is negative, it lies below the x-axis. And so your odd partial sums will now underestimate L and your even partial sums will overestimate L, but everything else about the theorem is still the same. So you always know that your error bound works in terms of the absolute value of the next term and so on. So let's go through our checklist. Do the terms alternate signs? Certainly. Let's convert over to the absolute value of the sequence of terms, and now we can just work with this. Is it true that the limiting value of an is 0? Well, yes. I mean, we know that n ln of n goes to infinity, n goes to infinity, and ln goes to infinity separately, so the product does as well. And of course, then when you reciprocate, 1 over n ln of n must go to 0. And is it true that the absolute value of the terms is strictly decreasing? So if you're in doubt, it is really worth just working on a little proof to convince yourself. You don't want to overlook something and sort of fall into a trap where you assume a hypothesis is true and it's really not. So you want to convince yourself. I'll mention one possible way of doing this is you could look at the function 1 over x ln of x and take a derivative and show that it's always negative. That would show that the underlying function is always decreasing, and so the sequence would have to be decreasing. But that's a lot more work than you need. You know that n plus 1 is greater than n, and ln of n plus 1 is greater than ln of n. In other words, the sequence n and ln of n are both strictly increasing. And so when you take the product of these inequalities, that tells you that n ln of n is a strictly increasing sequence. And if you just reciprocate this, that inequality is just telling you that 1 over n l of n is strictly decreasing because the next term is always smaller than the previous term. So yes, the three hypotheses are all satisfied, and so the alternating series test tells us this series converges. And then you could use the series to analyze partial sums and how close they are to the actual value of the series, and so on.